So today's topic is the multi-process service in CUDA. But before I talk about what that is, I want to provide a motivating use case for what problem am I trying to solve by introducing this topic for you today. So the question that I want to think about, and this is a pretty common topic in high performance computing, is suppose I have some amount of work to do, and I can choose to distribute that work among n MPI ranks, where n is some variable number of ranks. And so I have a couple questions that I could potentially answer given that framing. One question is, what is the optimal value of n, right? So given this fixed amount of work to do, how many ranks should I distribute this across? And then similarly, how many GPUs should I distribute these n ranks across once I've chosen a good value of n? And typically these two things are analyzed together. There are cases where you will just go with the kind of obvious thing, or the thing that is the most natural to do, which is to choose one GPU per rank, and then you basically pick as many ranks as you can, either to optimize like a weak scaling efficiency, and so you're basically just fitting as large of a problem per GPU as you can, or optimal time to, like fastest time to solution, maybe you're the thing that's driving you, and so then you just keep adding GPUs to your problem until you're not getting any faster, right? So you've strong scale to the maximum level. Those are both possible ways to distribute work among ranks and across GPUs. But let's just ask this question in the abstract, and then talk about how I would think about this in a simple case. And so for the simple case, I'm just going to write a very simple CUDA C kernel, and I've written the kernel here on the slide. So all I'm going to do is take an array and double it, right? So this is just a simple memory bound workload. The actual contents of the workload are not important. What matters is that the size of the workload scales with the size of the array, which I've unfortunately also chosen to call n in this case. So we have some array of length n, and we want to decide how many ranks am I going to distribute that across. And so let's think about what this problem looks like on a GPU. So if I have a screenshot here of Inside Systems, but I'm just going to actually show you an example profile of this problem live, and you can always just refer to the slide later if you want to. But this is a profile of CUDA C code that basically solves this problem. And this is the same code that I have listed in the exercise section, so you'll get a chance to look at it. But all it does is launch the same kernel a bunch of times in a row. So it's an extremely simple code. All it does is just launch this kernel that does doubles an array, and it does it 1,000 times in a row. So that's all it does. Trivial piece of code. If I zoom in to the Inside Systems profile, and I look at how long each individual kernel invocation takes to run, then I get a sense of how long it takes to solve this problem on one GPU. And for this case, I chose a problem size of 1024 cubed. So that's about 1 billion array elements. If you know that a double precision number is 8 bytes, then you also know that the size of this array in memory would be 8 gigabytes. And so that is already a pretty hefty fraction of the available GPU memory on a modern GPU. And so that seemed like a reasonable place to start, right? This is a problem that basically fills GPU memory, or approximately does, to within the right order of magnitude. And I just want to know how long does it take to solve this problem. So processing an array of length 1 billion takes about 19.7 milliseconds. That's how long this one took. This one is another 19.7 milliseconds. So that's a pretty consistent, right? If I look at any one of these, it takes about 19.7 milliseconds to process. So the question I want to ask is, can I make this faster by using more MPI ranks? And you all know, I'm sure, that if you were to distribute this across multiple GPUs, then probably you would make it faster, right? That you would just basically take the first half of your array and do it on GPU 0, and you take the second half of your array and do it on GPU 1. And then there would probably be some overhead to that associated with message passing. But as long as the array length is sufficiently large, then you would expect about a 2x speed up by doing that. Eventually, you would distribute it across so many GPUs that the message passing overhead became the dominant factor, because the compute would just be so short in relative terms. But just for a couple of GPUs or a couple of ranks, you would expect to see pretty good linear speed up. But the question I want to ask today is, what if I'm doing this on only one GPU? And I ask the question, can I solve this problem faster by using multiple MPI ranks on the same GPU? So I've not increased the amount of compute capacity available to me. I'm just distributing the problem across multiple MPI ranks on the same GPU. Now, so let's ask the question then, what happens when I have multiple MPI ranks targeting the same GPU? NVIDIA GPUs have several compute modes, and these modes determine how the GPU interacts with multiple processes running at the same time. The default mode that NVIDIA's GPUs come with when they ship to you is called default, and it allows multiple processes to run at one time. But we also have a mode called exclusive process, where only one process can run at a time. And this is useful in like shared environments where you might have multiple people on the same workstation, and you want to ensure that they don't step on each other. So in an exclusive process, if you try to run multiple processes on the same GPU at the same time, it will fail. And if like the second process to run will get an error message saying that the GPU is busy, please try again later, and the application will have to exit. But the default mode, where you just don't change anything, in the default mode, multiple processes can run at one time. And I made this point explicitly because I think this is actually a point of confusion in the community in some cases that I've seen, where people have the incorrect assumption that modern NVIDIA GPUs cannot do that. Well, in fact, they can. The thing that I'm going to introduce to MPS does not introduce any new functionality. You can already today use multiple ranks on the same GPU, and that just works. MPS, which I will discuss in a little bit, is a way of enhancing the performance of this scenario, but it's not really about adding new functionality, with some minor caveats that I'll explain later. Now, the reason I call this out, that we have multiple compute modes, and that this is a thing you should know about, is that different people might choose different modes for how they deploy. So in particular, on Summit that I know about, the thing that is given to you when you get a GPU is exclusive process mode and not default. And so it is a thing you have to opt into on Summit in particular, with an alloc flags option to bsub. But in general, this is something that OLCF opted into. In general, if you just got a GPU from the factory floor, it would be running on default mode to start with, and then you could run multiple processes at a single time. You can change this if you have root privileges on a server. And so that's why you can change this with a flag to bsub. You couldn't change this once you've already gotten an allocation, but there is a job flag on Summit to help you do this. And then there could potentially be other similar things at other centers. Now, let's then answer the question, if I take this problem and I just distribute it across some number of ranks, what happens? So I've given an example of how you might do this on Summit. I would do JS run, one resource set, some number of ranks, and then same number of CPU cores. And then I would distribute all of these ranks on a single GPU. And then this test code that I have in the repo just basically divides this problem size, which is 1024 cubed, by the number of ranks, and then distributes that fraction of the total problem size to each of the ranks. And so then I can ask the question, compared to the one rank case, what is the relative runtime of the multi-rank case? So I have a plot here of my measurements of that scenario for this problem. The vertical axis is the relative runtime relative to the single rank case, and then the horizontal axis is the number of ranks. And so higher is worse, because this is the relative runtime in like seconds. And so basically, for any number of ranks that is larger than one, we get about a 10 to 12% hit in additional runtime. But once I go above 2 ranks, I don't really change the scenario much. Up to about 20 ranks for this problem, I can keep on adding ranks, and I get the problem solved in about the same amount of time. So why would I do this, right? If I'm not making the problem any faster, why would I even want to consider this scenario where there are multiple ranks decomposing this problem? And the answer is that often you have like a legacy application that is not fully ported to run on GPUs, and you have some portion of the application that's running on CPUs. And so you want to distribute that CPU only part among as many MPI ranks as possible, while still taking full advantage of the GPU. And so what this is saying is that by default, this is possible with a slight hit in performance, right? You'll take like 10% for this problem, maybe a different amount for other problems. You'll take some amount of hit to performance from having multiple ranks coincide in the same GPU, but with the benefit that then the CPU only part of your application, if you have one, will be more evenly distributed across multiple ranks and therefore multiple CPU cores. Now, another way that this is commonly done is by using OpenMP threads instead of multiple MPI ranks. And if you want to learn more about that, you can refer back to the presentation that we gave in the last session in this series on OpenMP threading in CUDA. So how does this look if I do this? Well, let me go ahead and open up the NSYS systems profile for this case. So I've chosen 4 ranks on a single node. I did this on Lassen. So these are V100 GPUs, pretty much the same thing as I would have gotten on Summit. And okay, so I have 4 GPUs that I've profiled here. You can see each of the 4 GPUs in this profile. And I can then zoom in until I've kind of gotten down to the timescale of just a few kernels. And what I find is that by default, it looks like I have 4 kernels running at the same time. So each one of the ranks is simultaneously running its kernels. But then if I look at any one of the kernel's runtimes, I want to ask, what is the runtime of this kernel? This one, if you can see it on my screen, took about 25.8 milliseconds. This one took 18.8. This one on this other GPU took 25.7. This one takes 18.8, 25.7. So you can see like a kind of variation there. And so on average, we get about a 10% hit, right? That's what I was plotting in this plot before. On average, there's about a 10% hit to the kernel runtime, but you see some variation where in fact, some are slightly faster than the base case and then some are significantly slower, where the base case from the 1 rank case was 19.7 milliseconds. So that's interesting. And what this is telling us, or what the lesson that I take away from this is that basically what we're doing is on average, not making the kernel that much slower, but so we have taken for each rank, we have compared to the 1 rank case, we've given it a problem size that it's 25% as large, right? So it's a smaller problem, but on average, it takes about the same amount of time to solve. So why is that, right? Why is it that on average, it takes approximately the same amount of time to solve, even though each rank has a problem size that's only a quarter as large? And the answer is kind of obvious when you think about it, which is that I haven't changed the total amount of compute resources available to me. Right? The number of SMs on the GPU hasn't changed. And so every one of these 4 kernels that's running at any one instant in time has to be in some way taking away from the resources that are available to the other GPUs, right? There isn't any way that I can make this a better scenario, but in fact, it's even worse than that. So when I have multiple MPI ranks running on the GPU, what actually happens in this default compute mode, which is the one we're running on, is that every rank is independent of every other rank, and that at any given instant in time, only one of the MPI ranks is actually running on the SMs on the GPU. So suppose I have 2 MPI processes, process A and process B, and they're both submitting work to a GPU. If I look at what happens as a function of time, where each process is submitting some number of kernels, actually what happens is that at any given slice in time, I only have a kernel from either process A or process B happening, and then they will take turns in time. Now, if we look at the profile I was showing, this isn't obvious, right? NSYS systems is just showing us that the kernel starts at some big portion in time here and then ends at some time later. But what's actually happening under the scenes is that any given instantaneous slice in time on this timeline, only one of these kernels is actually making forward progress, and the other ones are kind of stalled, waiting for their turn. And so we're going to basically be swapping back and forth among these 4 ranks. So each of the 4 ranks will get 25% of the time on the GPU, but also is solving the problem that is 25% as large. And so to first order then, the amount of time it takes to solve each kernel doesn't change. It's about the same as if we had done 1 rank with solving a problem that's 4 times as large. Now, if you look on this slide here, I have this bit from the MPS documentation that says CUDA context. So I wanted to explain what that is as an aside. A CUDA context is a stateful object that is required for you to run CUDA on NVIDIA GPUs. And it's normally something that is transparent to you as the user. It's just created for you whenever you interact with the CUDA runtime API, or anything that sits on top of the CUDA runtime API, like Raja or Cocos or OpenMP or OpenACC. All of these things will, at some level, create a context, a stateful object that is needed to run on the GPU. The size of this object, however, can be somewhat large, or at least its size is relevant given the size of GPU memory. So on V100, on the V100s that are available to you on Summit, for example, on a Core GPU, there's 16 gigabytes of GPU memory, but on that same GPU, the typical size of a CUDA context is 300 megabytes. And a consequence of that is that even if we set aside the compute resources available on the GPU, the size of a context will will enforce some constraints on how many ranks you can fit on a GPU, right? Because we know that the size of a context is 300 megabytes. We know that there are 16 gigabytes on a GPU. So eventually, if we put enough ranks on the GPU, each one of them will have a context, and then we're going to run out of memory eventually, right? Entirely regardless of compute resources or even how much application data is used on each rank, we're going to run out of memory just on the size of these stateful objects. You can partially control the size of this context, and I'll come back to this in a bit later, but there is some irreducible limit below which you cannot go in terms of the size. And so that's always going to be measured in the hundreds of megabytes. And so that does place a constraint on how many ranks you can fit on the GPU in this default mode. So then getting back to this discussion I was saying about what's happening on the GPU, well, suppose I have three processes, A, B, and C, and they're submitting work to the GPU in this default mode. What's going to happen is A is going to submit its work, and then B and C are going to have to take turns. So if A doesn't have enough work to fill the GPU in a given time slice, then the remainder of the compute resources will be idle. So we've shown here kind of schematically, these little rectangles here are kind of representative of SMs. That's what they're supposed to be schematic of. And so A doesn't have enough thread blocks to fill all the SMs in the GPU, and so the remainder of the GPU will idle. If process B has some amount of work to do, which also doesn't fill the GPU, then it will take its turn on time slice 2 and also will not use all of the GPU. And then process C could potentially use the remainder of the resources or a good chunk of the remainder, but again, will have its own time slice completely blocked off. And so at any given slice in time, we are wasting a big chunk of the GPU resources for this case where each rank doesn't have enough work to fill the GPU. What this does guarantee is that any given process gets peak throughput at a given slice in time. It also guarantees full isolation between processes, but it does, as a consequence, mean that we are leaving some of the compute resources on the table. So then we could ask the question, when does oversubscription help? Is there a case where it's relevant? So let's run this same problem that I was looking at before, just doubling an array, but with a much smaller problem size. So before I was solving a problem size of 1024 cubed. Now I'm going to solve a problem size of 1024 squared. Let's take a look at the profile. Again, I'm just doing this kernel 1,000 times in a row. If I zoom in far enough, what I see now is that each kernel takes 22 microseconds to run. So that's consistent, right? It took about 20 milliseconds to run a problem that was 1,000 times as large. We've now made the problem 1,000 times shorter, and so it takes about 1,000x less time to run. But because we're now running on a timescale of tens of microseconds, that means that the gap between kernels becomes relevant. This is the time it takes to launch a kernel, right? Or measures something like that. This is a time measure. This measures how long it takes to actually get multiple kernels in succession running on a GPU. It's typically measured on the timescale of a few microseconds. So in this scenario, then, the launch latency, the amount of time it takes to actually queue up work on the GPU, can become a non-trivial factor. And so we might want to fill up the gaps in the timeline by having multiple kernels run simultaneously. That's a reasonable use case in which we might want to use multiple GPUs, or multiple ranks on the same GPU, right, to attempt to fill up this gap in the timeline. But actually what it turns out is that that doesn't help. So this is that same scenario, problem size of 1 million, distributed across 4 GPUs. And if I zoom in and look at any given chunk of the timeline, what I see is the following. What I see is basically that each kernel does take about a quarter, like roughly a quarter as long to run. So it's like 23 microseconds before, now it's like 6.7 microseconds. So I have made each kernel like something like 4x shorter by giving it 4x less work to do. But I have not solved the gaps in between the kernels. And in fact, I've made the gaps significantly longer. Right. So now the average, the majority of the time is spent not doing any work at all, and only small amounts of time are being spent on the GPU. So in other words, I did not solve my problem by adding multiple ranks to do this, right? I may have made each individual kernel faster, but I actually made the gap between kernels much longer. And this is a fundamental consequence of the time slicing nature of the algorithm, scheduling algorithm I just showed you, where the time slice is of the same order of magnitude or longer than the kernel by default. It's like typically measured on 10 to 100 microsecond time scales. And so as a result, we see that we're actually not getting any benefit at all. The time it takes to switch between processes now completely negates any benefit we could have gotten from theoretically overlapping kernels, such that the kernel on one GPU was filling in the kernel launch latency on the other GPU, right? This is just worse than this scenario. The majority of the time, at least in this scenario, was spent doing work. Only a minority of time is spent in this example doing work. Okay, so that's not better. So as a conclusion, this is all so far just talking about how GPUs work by default. I would summarize this as two conclusions. The first is what I would characterize as the no free lunch theorem, which is that if the GPU is fully utilized, I cannot get answers meaningfully faster. So if I looked at the large N case, 1024 cubed array, I did not really get a faster answer by using multiple GPUs. And the reason is that, and I could not, right? I really could not. There's no scenario in which I could, because in either case, the amount of work that each rank has is enough. Each rank has enough thread blocks to fully saturate a GPU. And so if that's true, I can't get any faster, right? Adding another rank doesn't help me. It cannot make me faster because each rank already saturates the GPU. The only case where I could imagine even theoretically getting a speed up by using multiple ranks in the same GPU is for cases that don't fully utilize the GPU, right? That don't launch enough blocks to saturate the GPU. But this doesn't often work out right for GPU only workloads, right? And the example that we gave was a demonstration of that. But in general, I would say it works out less often than you would think, just because the timescales are so short for these short workloads that latencies associated with launching the work and other related things end up becoming a pretty important player and may negate any benefit you're trying to get. I'm not saying it doesn't exist, just that there are a few cases that I've seen in the actual real world where it's true. But a case where this is much more relevant is the kind of example I gave before, where you have a legacy workload that has some CPU only work and there's nothing you can do about it. And so if you have that constraint, then making the GPU part as fast as you can, given that constraint, could be a reasonable thing to try to do. So how could we do better? Well, the case that we've been looking at so far is the case on the left, preemptive scheduling system, where at any given instant in time, only one process is running, and then we switch among time slices, going from time increasing from left to right. And so that has the problem or the limitation that if any one chunk in time slice doesn't have enough work to saturate the GPU, I'm just leaving performance on the table. So a thing that I could want to do instead is have concurrent scheduling, where processes A, B, and C are all running at the same instant in time, and then sharing SM resources to do compute together. So this concurrent scheduling scenario could improve the case that I've been looking at. So that's what MPS is intended to solve. MPS, or the multi-process service, is a piece of technology that NVIDIA offers that allows us to instantaneously, at any given instant in time, share compute resources among the multiple ranks. In particular, they can share SMs together. So the idea is that we can concurrently map multiple MPI ranks onto the same GPU, whereas without MPS, we will run into the scenario I showed before, where the ranks take turns. At any given instant in time, we are not concurrently having execution among multiple MPI ranks. And again, you typically would use this when a given rank is too small to fill the GPU on its own. So how does this improve in detail on what we had before? Well, the way it works is that rather than each MPI rank submitting to its own CUDA context and then having each CUDA context submit work to the GPU, we create what's called an MPS server. And that server then accepts work requests or kernel launches from each of the two MPI ranks. And then that server context is responsible for distributing the work among the GPU SMs. And this context, or this server, MPS server, is where all the magic happens to distribute work so that multiple MPI ranks can be running concurrently. And so that at any given instant in time, I could have kernels from multiple ranks running at the same time. And that's what I'm showing here. And then this allows a scenario where at any given instant in time, I can have multiple ranks space sharing the GPU, right? So this is the ideal scenario where at any given instant in time, I'm sharing in space, you might say, the SMs that are distributed across the GPU chip. So this will allow me to get maximal usage out of the GPU. Okay, so with MPS, we get a multiple ranks using the same GPU at the same time in terms of instantaneously using all the SMs. What does that mean for my example case? Well, this is some data from the same problems before. This is a large N case, 10 to the 9, 1024 cube. And I'm distributing that problem across multiple ranks. And it turns out that actually now I've completely recovered the performance loss, where I do not take any performance hit by having multiple ranks, up to about 20 ranks for this problem anyway. So it turns out that all of the performance loss that we saw before for this case, where we were having multiple ranks split a large problem, was due to this context switching scenario where the GPU was at any given instant in time had to switch back and forth between ranks. And the overhead of switching between the CUDA context, the multiple MPI ranks, was what was hitting our performance. MPS does this automatically for us in hardware, starting from the Volta generation of GPUs. And so it's completely handled for us in hardware, not in software, and multiple ranks can be running concurrently. And so the upshot is we basically recover all of the performance loss. And actually, in this case, it even becomes slightly faster. It's like 1% faster. There's nothing really profound about that. It's just due to the kind of quirk of this particular problem. But the point is that we can recover the performance loss. But the conclusion there changes as we make the problem smaller. So in this case, right, this is a problem with an array of length 10 to the 9. And so if we distribute it across 20 ranks, you can just do mental math, right? The amount of work per GPU, the length of each array is still 50 million, right? Assuming I did that math right. 50 million is still a large enough amount of work that saturates the parallelism on a GPU. And so at some point, I could have added enough ranks that I would have distributed this across too many, and I would start seeing the story change. But we can also just see the story change with a smaller base problem. So if I make the problem size 20 million, then whether or not there is an improvement starts to change. And so I ran this case from 1 rank to 20, and my finding for this case was actually kind of inconclusive. So what I plotted here is the average runtime as a function of number of ranks for this problem. But I also plotted error bars because what I found is that there was actually quite significant variance in how long it took to solve this problem and as a function of rank. And so in some cases, I got a slight speed up. But in many other cases, I saw a significant slowdown. And the median case was a slowdown, significant slowdown of like 10% or more. And so this is kind of starts to become on the edge where like, I don't have enough work now per rank. And so the latencies associated with launching small amounts of work start to negate any benefit that I had from having multiple ranks work together to help fill in those gaps in the timeline. And then if the case is much smaller, then it's just a clear loss where, so like in this case, there were lots of there were plenty of runs where it got faster, right? Like 10% faster, but then there were other cases where it got a few percent slower. But if I make the problem sufficiently small, then this scenario is just a total loss, where I could get 7x slower just by going up to 20 ranks. And this basically becomes the case where the work per kernel is so small and the overhead from launching the kernel becomes such a dominant factor that it's just a total loss to try to distribute this problem across multiple ranks. So hopefully that answers the question in chat about how this scenario changes as a function of problem size. When the problem size is large enough, MPS can help you distribute the problem without any loss in performance. And in some cases, it can actually make it faster. But then there are other cases where, especially as the problem size gets sufficiently small, where distributing across multiple ranks doesn't help you, because then the work per kernel launch just becomes too small. Another question, should you always use MPS? Or I'm sorry, I read the question backwards. Should you always use MPI with MPS, or are there other APIs that can use MPS? So MPS is completely agnostic to the programming model. There's nothing about MPS that knows about MPI, quote unquote. And so you can use it for any programming model that can have multiple processes running on the same GPU. So like SHMEM programming models, like PGAS models, could also work on and use MPS. Doesn't even know about MPI. It's just that MPI is the kind of most common use case for this audience. So in conclusion then, the no free lunch theorem still applies. Basically, you can't get faster answers in general just by using MPS, right? If your problem is sufficiently large, then you should just run a single rank per GPU, and that's, you're good to go. You should, in general, strive to write your applications so that you don't need MPS, right? That is the goal. You should have enough parallelism in each rank so that you don't even need to answer this question. However, there are cases where you cannot do that, either because of the problem size, you just can't make it that large per rank, or you have some other constraint, like some fraction of the runtime is still happening on the CPU. And so in order to maximize the performance of that scenario, you have relatively small workload per rank. And in that case, MPS can usually help you and compensate for some of that performance loss. But you should always profile your code to understand why MPS did or did not help. There is no rule of thumb that I can give you. Well, I can give you some heuristics, but I cannot give you like an ironclad rule, which says this is a scenario that MPS can or cannot help. I cannot make that prediction because GPUs are complicated and the schedulers are complicated. So you should, in general, profile your code and just try it and see, rather than try to reason it through. And I say this because I often have people ask me, like, when will MPS help? Right? And the answer is, in general, just try it and see. That's what I can tell you to do. A side note that I will add is that MPS has changed historically. So it wasn't always the case that it worked as efficiently as it does today. In particular, there is on previous GPUs, particularly Pascal and previous generation GPUs, we didn't have it as an efficient a hardware scheduling mechanism for MPS. And so there was non-trivial overhead for using MPS on Pascal and previous generation GPUs. So the scheduling was basically happening in software. And so that meant the latency of kernel launching tended to increase. And so there were some inefficiencies there. On Volta and later generation GPUs, kernel launches are basically streamlined through hardware. And so you don't really take a performance penalty from having MPS on. You could probably use it in general in production, even on a single rank, and it wouldn't change anything. But obviously you want to use it in the case where you have multiple ranks targeting the same GPU. Also on pre-Volta GPUs, there was limited isolation between processes, and there were a limited number of clients per GPU, so you can only have as many as 16 per GPU, whereas on Volta you can have 48. And also there was no notion of provisioning resources among the processes. So you couldn't do anything like control how much of the GPU each process used, which is available on Volta, and I'll talk about in a moment. And so this is kind of a summary of that in text form. I'll just leave this here for your reference later about the differences between pre and post VOLTA. But my assumption is that almost all of you are running on VOLTA or later GPUs. And so I will not talk too much about that. Okay, a question in chat. Does MPS apply to multi-thread situations? Well, MPS applies to any scenario in which you would have multiple contexts, CUDA contexts, submitting work to a GPU. And so the reason why that's a useful distinction is that in most cases where people use multiple OpenMP threads, they actually are doing it all with the same CUDA context. So if you do the naive thing, the thing that Robbie taught you in the last lecture, where you have multiple OpenMP threads submitting work in the same CUDA application, and you're just using CUDA runtime API, actually you're just using a single context. And so MPS isn't relevant for that scenario because there's only one context to begin with. However, it is possible to write an OpenMP threaded application or some other threading model like pthreads, where each thread explicitly controls its own CUDA context, where then MPS would become a relevant factor. But that's not the common case. You typically don't see that in user-facing applications. There are some GPU backends where that becomes a relevant factor, but for most people, the answer is basically the CUDA context already is multi-threading aware. It can do that. And then we have a separate approach for handling that, where in recent versions of CUDA, we've been trying to get the overhead down from submitting multiple threads, submitting work to the same CUDA context. Now, a couple people asked the question, and this is a true limitation, that there is fairly limited support for debugging when you're running under MPS. That is a limitation to be aware of. And this is basically because then it becomes hard for us to, at the hardware level, attribute specific individual kernel workloads to individual specific processes. And so the notion of like attaching to a process and then just pausing that process's work becomes basically not possible. And so the debuggers have fairly limited support when MPS is running. One thing you can do that is supported is to drop a core file using CUDA GDB's ability to drop a core file when an error occurs, but actual like on-demand debugging is generally not supported with MPS. And so that is a limitation to be aware of. Other than that, there aren't that many relevant limitations. You can use the profiling tools with MPS. You can use like compute sanitizer with MPS, but there are some debugging related implications. And other than that, it turns out that MPS is basically completely transparent. So you don't really write your application needing to know about MPS. You write the same application either way. And all you do is start a server, or rather a daemon, which I'll talk about in a moment, that then transparently handles this for you. So a MPS control daemon is what has to live on your server on the node, and then can spawn MPS servers, which are the things that then accept work from your MPI ranks. So the way that this works in detail is that on your server, you would run the daemon NVIDIA-CUDA-MPS-control. And this is just the thing that would then automatically spawn servers to accept work on GPUs. Now, on some platforms, you don't actually have to do this explicitly. So for example, on Summit, you can do bsub-alec flags GPU MPS, and that will start the server for you. But on basically any platform, you can just start this manually if you want to. And so it doesn't require root to use this. And so you can run this on any platform you want to, and that will allow you to have multiple work running at the same time. So that's what you need to do to start it. And then once you do it, your application just run natively, and in some cases get a speed up. Now, it's often recommended, like you see on the documentation, it's often recommended to set your GPU to exclusive process mode before you do this. And the reason we typically recommend that is that you want to avoid the scenario where multiple people are trying to run on the same GPU at the same time, because MPS doesn't really enable that. Like, you can't actually have multiple users at any given instant in time running on the same GPU. And so this helps avoid the scenario where people try to start multiple MPS servers on the same GPU accidentally. And so you might want to avoid that. But it's not required to use exclusive process, it's just recommended. And it's completely irrelevant in many HPC like Slurm or LSF contexts where you have exclusive access to a GPU anyway, in most cases. So you don't need to worry about it, but this could be relevant on like a workstation environment. There are some environment variables that are relevant for you when working with MPS. I won't go through these into detail. The one that's the most relevant for you is the one called CUDA MPS active thread percentage. And this controls what fraction of a GPU can be used by each process. And so the way that you use this environment variable is set CUDA MPS active thread percentage to a number between 0 and 100. And what this allows you to do is basically limit the total amount of SMs that can be used by each process. And so if you set it to 100, then each process can use as many as 100% of the SMs. If you set it to 10, then every process can only use as many as 10% of the SMs. And so this allows you to guarantee resource provisioning, right? Because it means that a given process cannot exceed the number of SMs that you've allotted to it. So it sort of guarantees a quality of service, but there are some limitations. In particular, it doesn't change no free lunch theorem, right? So if you give each process 100%, which is the default, then there will still be some contention among SM resources, and so they're going to have to take turns. And also, this is only a limitation on SM utilization. It doesn't control memory bandwidth or memory capacity. So you still have to be careful that you're not using too much memory on the GPU. And also prior to CUDA 11.2, this environment variable had to be the same number for all ranks. However, since CUDA 11.2, which isn't really deployed, the driver for this isn't yet deployed on most of the DOE systems that I'm familiar with. However, at some point it will be true that you can have a different process, a different percentage for each process. And so you can imagine having a scenario where, like, the left is what's available to you today, where you could set each one of these to 33%. And then process B in this scenario can only use 1/6 of the SMs. And so you would have 1/6 of the SMs be just not used, they would be idle. But if process B later in time had more work to do, then it could guarantee that it would fill those remaining slots. Starting from CUDA 11.2, you will be able to set different different value for this percentage for each of the different ranks. And so you could set, for example, 100% to C in this case, so that it could it could expand to fill the unused resources that B was leaving behind in this scenario. And so this is useful for some cases where the amount of work is significantly variable between processes. Not a common thing for like most MPI workloads, but there are other workloads where this might be relevant. Some things to watch out for are that, so I started by pointing out that the size of a CUDA context is non-negligible. So measured in the hundreds of megabytes per process. A significant fraction of the context size, in fact, typically about half, is allotted to per thread local memory. So in CUDA, you can have private per thread local stack memory. And the amount of stack memory per thread is 1 kilobyte by default. But what CUDA does to back this is that actually this local memory is backed by DRAM. And so when you start up your application, CUDA has to reserve 1 kilobyte per thread times as many possible threads as can be simultaneously resident on the GPU. The maximum number of threads that you can have resident on an SM is 2048 on basically every modern HPC GPU. And so if you multiply 2048 threads per SM times 1 kilobyte per thread times the number of SMs, you'll get about 160 megabytes of stack space reserved in DRAM on V100 and over 200 megabytes in A100. And so this can quickly add up, and it's part of why there's a limitation on how many ranks you can fit per GPU. But if you use CUDA MPS active thread percentage to reduce the number of SMs that each process can use, then CUDA doesn't have to reserve as much stack memory because it only needs to reserve as much stack memory as possible threads that could be running. And so if you reduce the number of SMs that can be used by a process, you don't need to have as much stack space reserved. So this can be a way to control the memory footprint from growing too rapidly, but also, of course, then limits the amount of compute that you can use on each process. And also, CUDA device max connections is not a commonly used thing, but I just have listed that there in case you're familiar with it. If you want to learn more about that, you can ask me about that in the Q&A, but I'll just leave that there. Final thing that I'll say is just that starting from the A100 generation of GPUs, we've introduced this concept of MIG, or multi-instance GPU, which allows physical partitioning of a GPU. So with MPS, you have dynamic contention for resources, but it's one server that accepts work from multiple ranks, and then that server then distributes work across the available SMs on the GPU. And so a consequence of that is that there isn't really guaranteed, or there is a limited amount of how much you can guarantee in terms of quality of service or execution provisioning. With multi-instance GPU, you can directly control both SMs and also memory, and then distribute that across multiple slices of a GPU. And so you could have multiple different processes running for multiple users at the same time. And this is relevant for the A100 GPUs and is not super relevant for many HPC use cases, as far as I know. There are use cases in like AI inference where this becomes more relevant, where you might want to have multiple inference processes running at the same time. So that's a common scenario where this might be relevant. But if you do use MIG, because I think some of the HPC centers will be exposing this eventually over time, this could become relevant for you to know the differences. And with MIG, you can basically divide an A100 GPU into as many as 7 different instances that has dedicated SM, cache, and memory resources. And so you could have as many as 7 different users running 7 different workloads on that GPU. Again, limited usefulness in like the typical HPC scenario where you have a GPU to yourself anyway, but there are some use cases where this might be relevant to you. And to summarize the differences, with MPS, you have logical partitioning of the GPU, but with MIG, it's physical. And so that guarantees some isolation between processes that you wouldn't have with MPS. So for example, with MPS, one of the major caveats is that if an error occurs, like an illegal memory error or some other sticky error that brings down a process, that's going to pollute every process running on the GPU. And that is probably what you want in like a typical MPI scenario, because MPI generally we're not running in a fault tolerant scenario anyway. And so if one rank dies with some error, you're probably going to be crashing anyway. But there are some workloads where you do not want one process coming down for bringing down every other process, especially like in multi-user environments. And so MIG provides you that. And again, it also provides you, because the memory is fully isolated between instances, that also guarantees like memory bandwidth provisioning as well as and memory capacity provisioning as well as compute provisioning. To answer the question in chat, yes, you can use MPS together with MIG. So if you have a GPU instance, you can that is fully composable with MIG with MPS, and you can have an MPS server running on that MIG instance. Okay, so that's MPS. I'm happy to take any questions, and I hope this was useful for an understanding when and where MPS might be relevant to you.